Resonance in AC circuits. An AC circuit is said to be in resonance if the circuit behavior is purely resistive. This happens when the inductive and the capacitive reactances cancel each other in the circuit. That is, the J component of the complex impedance or the vector impedance of the circuit is equal to 0. As a result, the current and voltage vary in phase with each other in a resonating AC circuit. Thus, the power factor equals unity. In this section, we shall discuss the two important types of this phenomenon of resonance, namely series and parallel resonance. Series resonance. Consider a series RLC circuit as shown in figure 1.17a. Its impedance Z is given by Z is equal to R plus J times XL minus XC with XL is equal to omega L and XC is equal to 1 by omega C, where omega is the angular frequency of the input AC. Figure 1.17a shows typical series RLC circuit under construction. The variation of XL, XC, Z and R with respect to omega are shown in figure 1.17b. By definition, we know that under resonance, magnitude of the impedance Z is equal to R. This means that magnitude of Z is equal to square root of R square plus XL minus XC whole square is equal to R. Thus, the current I and the voltage E of the circuit are given by I is equal to E by Z, which is equal to E by R, or you can also express it as E is equal to I into R. This implies that the resonant AC circuit is purely resistive. Under this condition, the typical phasor diagram for the circuit is shown in figure 1.18, where figure 1.18 shows the phasor diagram for the AC circuit under resonance. Here, the circuit is behaving purely resistive. The frequency at which the resonance takes place is known as resonance frequency, denoted by F0, and the corresponding angular frequency by omega naught. The current in an RLC circuit varies in accordance with the equation given by I is equal to E divided by square root of R square plus XL minus XC square. Initially, at lower frequencies, XL is less than XC, since XL is directly proportional to frequency F, and XC, which is directly proportional to 1 over F. As F is increased, XL goes on increasing while XC goes on decreasing. As a result, I increases with respect to the frequency F. In this region, obviously the current leads the voltage. This trend continues till F becomes equal to F0 when XC is equal to XL and I reaches its maximum value. Under this condition, we have XL is equal to XC or omega naught L is equal to 1 by omega naught C, because omega is equal to omega naught. This implies omega naught is equal to 1 by square root of LC, or if you substitute for omega naught as 2 pi F naught, you can express F naught as F naught is equal to 1 by 2 pi times square root of LC. If F is increased further, XL dominates over XC and therefore I follows a decreasing trend with respect to the frequency F. And in this region, obviously the current lags behind the voltage, which is depicted in figure 1.19, where figure 1.19 gives the graphical description of the variation of current I with respect to the input frequency and the phenomenon of resonance. The variation of I with respect to R is shown in figure 1.20. It is seen that the variation of R does not change the resonance frequency of the circuit, but the maximum value of the current, that is I max, changes with R as shown in figure 1.21. Where figure 1.21 gives the variation of AC voltage across inductor L, C and the resistance R as a function of L time resistance and L Emax are the values of L corresponding to resonance and the maximum voltages across L respectively. At lower values of resistance R, current I increases more rapidly with respect to R. Hence, the circuit is said to be more sharply tuned at lower values of R. You can see diagrammatically here. At relatively larger values of R, the circuit is said to be more broadly tuned. Let's discuss regarding the half power frequency. We know that the frequency response curve of an AC circuit is symmetric about the frequency F0 of resonance. At resonance, the power P of the circuit becomes maximum, which is equal to E square by R. As we also know, the impedance Z of the circuit is given by Z is equal to square root of R square plus XL minus XC square. In this equation, when R square is equal to XL minus XC square, we can write Z is equal to square root of R square plus R square. Therefore, Z is equal to square root of 2 into R. Substituting this value for I, we get I is equal to E divided by square root of 2 times R. Therefore, power P is equal to I square R, which is equal to E square divided by 2 times R square, which is half the power at resonance. As shown in figure 1.12, there are two frequencies F1 and F2 at which equation 36 is satisfied, so that the power at these frequencies are equal to half of the maximum power. Hence, the two frequencies at which the power of the circuit becomes half of its maximum power are called the half power frequencies. F1 and F2 are respectively called the lower half and the upper half power frequencies. The differences between these two frequencies is known as the bandwidth of the circuit. Figure 1.12 gives the graphical meaning of half power frequency, that is F1 and F2, and the bandwidth of AC circuit. The expression for half power frequency may be obtained as follows. We have XL minus XC is equal to R at lower and upper cutoff frequencies, that is F1 and F2. At the lower half power frequency, XC is greater than XL, so that XL minus XC is equal to omega 1 L minus 1 by omega 1 times C, which is equal to minus R, or we express omega 1 as minus R by 2L plus or minus square root of R by 2L whole square plus 1 by LC. Usually R by 2L whole square is much less than 1 by LC, so that the above expression may be approximated as omega 1 is approximately equal to minus R by 2L plus or minus square root of 1 by LC. Therefore, F1 is equal to minus R by 4 pi L plus or minus F0, where F0 is equal to 1 by 2 pi times square root of LC. Since frequency cannot be negative, we write F1 is equal to F0 minus R by 4 pi L and F2 is equal to F0 plus R by 4 pi L. The bandwidth is therefore given by F2 minus F1, which is equal to R divided by 4 pi L plus R divided by 4 pi L, which is equal to R divided by 2 pi L. This circuit is said to be sharply tuned if the bandwidth is small. From the above equation, it may be seen that bandwidth depends on the ratio R by L. Thus, this ratio R by L indicates the sharpness or the sensitivity of the circuit. The ratio of F0 to bandwidth is called as the quality factor of the circuit, denoted by the letter capital Q. So, we have quality factor Q is equal to F0 divided by bandwidth. Substituting for bandwidth in the expression for Q, we get Q is equal to omega naught into L by R. Therefore, Q is equal to 1 by R times square root of L by C, where omega naught is equal to square root of 1 by LC. From this equation, it is clear that Q is indicative of sharpness of the circuit. Thank you.